Good afternoon, everybody. As introduced, I'm Eric Hall, President of Hall Incorporated. Hall Incorporated is a specialist in advanced composite structures with factories in Bristol, Rhode Island, Breskins, Holland, and Auckland, New Zealand. Hall Spars and Rigging, as the name implies, is a supplier of masts and rigging to the sailboat industry. Hall Composites services a number of industries, including aerospace, military, architecture, and renewable energy. The point of my discussion today is to give you some ideas for innovating ways to improve structures with advanced composites. First of all, I think for the purposes of the talk, I'd like to give you my definition for this talk, advanced composites. Advanced composites basically is using pre-impregnated materials, heat cured under high temperature and high pressure. The pre-preg materials are materials with the fibers in them pre-impregnated with heat cure epoxy, and the advantage with pre-preg materials is you have a very well-defined resin content, so that you can, if you make a layup, design a layup, and you know what the resin content and the weight is, when you finish the layup, after it's cooked, you weigh it, it's almost exactly what you designed it to be. The second advantage of pre-preg materials is the fibers are put together in very, very straight lines, and these in composite structure, the straighter the fibers, the stronger and stiffer the material is. For instance, if you have a composite structure with wavy fibers in it, it's not going to be as stiff or as strong as one with these perfectly straight fibers that the pre-preg materials give us. Second aspect of advanced composites, as we define it for this afternoon, is autoclave curing. Autoclave curing is done at high temperature. We mostly cure at 120 C. However, some of the aerospace applications have to be at a higher temperature, usually around 177 C. We also cure at very high pressures. 6 bar, 6 atmosphere is generally what we use for solid laminates. We use 3 bar on laminates that are cored structures, because the core, even aluminum honeycomb, cannot stand the pressures of 6 bar. What autoclaves do for you is give you lasting quality in the laminate, longer fatigue life, and superior reliability. The first thing to say about autoclave curing is it eliminates voids in composite structure. It's kind of like, a close metaphor is it'd be like one way vacuum bagging might be to put a bunch of wood together, put glue on it, and just lay them on top of each other. With the autoclave, you add the clamps, and that really makes a much better structure. So autoclaving pressures the laminate elements together and makes them a better bond, and it also reduces voids. If you look on the left-hand side of the graph, that's bars pressure. 1 bar pressure is effectively a vacuum bag pressure laminate, and you can see that the void content in percent is something like 3.5% round numbers, and voids are little air bubbles that are very similar in concept to inclusions in cast products. If a cast product has a lot of inclusions in it, these inclusions can cause weakness or breaking, and the same thing, these little micro bubbles in laminates, their edges are very sharp and they can cause slow delamination. So you want to eliminate voids wherever you can. If you look up at the 6 bar end of this thing, you've got voids that are basically 10% of the 3.5, in other words, down in the 2, 3, or 4 tenths of a percent, and that's a big difference in strength and stiffness. Again, you can see the blue curve is flexural strength. Again, the flexural strength is lowest at vacuum bagging and highest at 6-bar pressure. And there's a 10% difference improvement in the stress levels to failure. And they really do make stronger laminates with the autoclave curing. Just to give you an idea of what happens with carbon fiber structures, these graphs will show you unidirectional. In other words, all the fibers going in the same direction in a laminate. And you can see with stiffness, interestingly, I found this out a long time ago and it was interesting to me, but you'll see that titanium, stainless, and aluminum all have the same stiffness to weight ratio. Aluminum is 1/3 the stiffness of steel, but it's also 1/3 the weight. So the stiffness to weight, and the titanium has similar properties. But the carbon stiffness to weight is 5 times that of aluminum or stainless. So for the same stiffness, you're 1/5 the weight, and that is really makes a big difference in a lot of products. If you're making tubes like masts, not all the fibers are going in the same direction. They're crisscrossed, and so the laminate isn't as sort of relatively strong. But when you make a tube, that's the way you have to make it. But a tube is, for the same stiffness, it's half the weight of aluminum in just standard modulus material, and we have standard modulus, and then we have higher stiffness, medium modulus, high modulus, ultra high modulus. And as you go up in the modulus, your difference from aluminum increases from half the weight down to maybe 40% the weight, just using rough numbers. So either way, whether it's in a laminate or unidirectional, carbon fiber really has some dividends. Tensile load, again, this is just unidirectional. Again, you got about the same tensile weight to strength ratio, much higher, in this case 3-to-1. If you make carbon rigging like the pictures show here, the advantage is again that 5-to-1, so that the carbon rigging weighs 1/5 the weight of the rigging we used to put on boats with nitronic 50 rod rigging. If you have a laminate, the difference reduces, but a good way to think about it is that a carbon tube that's got the same stiffness as an aluminum tube is half the weight of that tube, but double the breaking strength. So you have basically a specific strength of something like 4 times. Thermal stability is interesting. Aluminum, when it heats up, the thermal expansion expands pretty readily. Steel expands pretty well. I'm not so sure. We've never used concrete on mass, so I'm not really sure about that one. But carbon epoxy has coefficients of thermal expansion very low, and in some cases, as we show here, there can be -1s. In other words, as normally when stuff cools, materials cool, they slowly contract. I think it's easier to remember that materials expand with heat. They get bigger when you heat them up. Some carbon epoxy laminates actually get bigger as they cool down, and that helps us make our masks, which are done on male mandrels, so that the material is put on the aluminum or a composite mandrel of equal coefficient of thermal expansion. So when that is put into the autoclave and cooked at elevated temperatures, the big mandrel inside stretches, and in our autoclave length, which is 46 meters, you can actually measure inches difference. And what that does is pull everything tight, all of the fibers even tighter than they were, which is again making them straighter. And then what happens is when it all cools down and everything gets back to room temperature, that aluminum mandrel is much contracted again, but the carbon hardly has contracted at all, and in some cases actually might have gotten a little bit bigger. So that helps us pull this big piece of carbon tube off the mandrel. Marine environment, the composite structures are basically virtually corrosion free. We do have to put metal together with our carbon fiber. You put aluminum together with a carbon fiber, especially, and if you put stainless, both of those are dissimilar metals to carbon, and if you don't really insulate them, you can get bad corrosion with carbon. You can get readily, with the aluminum, you can get very, even a fair amount of rust, a surprising amount of rust with stainless steel with carbon, again, if they're not properly insulated. One of the materials we like using best is titanium. They're just not dissimilar. Titanium is not dissimilar at all with carbon fiber. I'll show you, we'll go back. These fittings on the rod rigging, we make all in titanium, and we have no issue with any kind of corrosion, whatever. Meanwhile, you got a benefit that titanium is about half the weight of stainless, so it's a double bonus. But titanium is really the material to use with composites, and these days it's not that much more expensive. The only difference on a machine part is really the price of the material, which really isn't that much. So now we're starting to talk about what Advanced Composites has done for us and is doing for us today. But first, a look into the past when Advanced Composites was still pretty much on the cutting edge. In the late 60s was my first job, was at Grumman Aerospace, and it was my great fortune was to be on the team that designed the F-14 aircraft. Anybody that hasn't been introduced to the F-14, they really have, because I don't think anybody in the room has not seen Top Gun, and Top Gun's star of the show was the F-14. And we designed this aft stabilizer with a boron composite skin as a testing prototype. And by the time I had left Grumman, and that'll come up in a minute, this was still something that was being tested, and that they basically designed the aircraft for a titanium skin. But the test worked out so well that Grumman said, we're putting boron composite stabilizers on every F-14, which they did. Interestingly, today we fly around in all these Airbuses and Boeings, and everybody knows, or most people know, that they're filled with different composite parts now, all being done in production. This was the first time in the history of aircraft that the first plane that ever had a production advanced composite part made on a production basis that for a production aircraft. Today, you don't even think about it anymore. Shortly after Grumman, I left and went to work for a yacht designer who was redesigning Intrepid for the America's Cup defense in 1970. And through my connections at Grumman, we developed a very, very advanced spinnaker pole, even by today's standards. The spinnaker pole had boron fibers lengthwise and crisscross with carbon fibers, all of which were very, very expensive materials then. I mean, today we talk about carbon fiber costing between $15 and $50 a pound. And in 1970, carbon cost per pound $300, and you can imagine what that would have been in today's dollars. And the boron is over the top even today. It's not being used. But this spinnaker pole really changed the game for these guys on Intrepid. The Intrepid standard spinnaker pole weighed 89 pounds. Okay, we'll use pounds here, but you can tell the difference. This thing came in at 39 pounds, and that foredeck guy could handle it all by himself, where the other pole, there was no way he could do it. And so it was a big, big advancement. And today, carbon spinnaker poles and carbon everything in sailing yachts is just completely routine. But it's interesting how we took those that product or that system, Advanced Composites, and uniquely solved some and improved some structure back then. Today, there are a lot of examples, an awful lot of examples of innovative ways to improve carbon structure. And again, as I said, I'm going to just show you a few just to give you examples and maybe give you a little bit of inspiration on what can be done. one of the most interesting things we've done in a long time is make the carbon fiber keel box for Hodgson Yachts, who built Comanche. Comanche, a lot of you know, is one of the most extreme and fast and exciting boats that's been built in the last couple of years. This boat has to sail on the ocean in any kind of weather. It's already been in one Sydney Hobart race, and they're going to go in the next one this year. This boat has a canting keel, so you can imagine big waves, canting keel. That keel box has got to be right on the money. And the only way that the designers of the boat really expected this keel box to work for them the way it should work was to autoclave cure it, and they basically gave us the job to do that. And that's worked out very, very well. We, as I said, Hall Composites side of the business services the aerospace industry. We are making aero ramps for the sides of the SpaceX rockets. You can see the arrow. With this part that the technician is working on here, the arrow points to it on the SpaceX rockets. SpaceX rockets are going regularly to the International Space Station, delivering supplies and other things for the International Space Station. These are made maybe when we went to the moon, stuff like that on the side of the rockets would have been made out of metal. Now this is made out of carbon fiber, some glass in there, aluminum honeycomb. Interesting with these is we finish them off with thin 3mm cork, and the cork is there to protect the carbon fiber structure from ice chips falling off the rockets. As now, the fuels in these rockets are very, very, very cold, and they create ice on the top, on the sides of the rockets until they take off. And I think you can see showers of ice coming off the rocket in the picture here, and those pieces of ice tend to hit these things, and if you don't have them with cork covers, they can damage the composite. This is a underwater generator system with helical blades. The best way to describe this is these things look like the old hand lawnmowers, and they're the blades are both curved and twisted, so they're helical in shape. And this would not have been possible as in a realistic basis if you made those vanes out of steel or rotors out of steel. Firstly, there'd be a real problem to machine. If you had to machine them out of a solid block, you can imagine how big the block is to begin with. If you had to weld it all up, you'd know that anybody that's worked with welding, you know you'd have to worry with twist and deformation and everything like that with welding. With composites, they can just fit any shape when you start. So you put them in the mold. You can see this is a twist, how the mold not only bends but twists. But the material, when you put it in, doesn't care what the shape of the mold is. You just put it in, you cook it, and then all of a sudden it comes out a nice solid product. These things are very, very good in fatigue. As we said before, corrosion resistant. You don't have to worry about that. And it really makes a good product. This particular thing is meant to be used in the Bay of Fundy, and it's operating with current. In other words, no matter where the flow is going, these are always going in the same direction. And for 6 hours, the current is going one way, 2 or 3 knots, and then 6 hours back the other way, and completely predictable. It's not like a wind vane where it really works well when it's windy, and if there's no wind, it doesn't work at all. This works every day the same way. But the combination of the ability to make these things and the fact that they're corrosion resistant and probably way better in fatigue makes this product able to be made because of advanced composites. We also make stuff for Boeing via Zodiac Aerospace, not related to the inflatable ribs, but basically we make this in a matched mold, and this is an example of parts that can be made in pretty high production levels. If we cook something in the autoclave, it's basically the autoclave table rolls in at about 3:30 in the afternoon, and the next morning you take it out. These are made in heated match molds, and one comes out every hour and a half. But basically, it's interesting. You put on the match mold. It's just 2 pieces or 3 pieces of carbon and glass, a piece of 1/4-inch Nomex honeycomb, and then again a couple of pieces on top of that, just sitting on top of the mold. Then you close the mold on it. It's kind of like a waffle, and it cures for an hour and a half, and out comes something that looks like this black thing. There's work to be done. We put aluminum picture frame on them. Zodiac finishes it off with the rest of the assembly. But they're all very, very precise and completely repetitive. So that's just another method and a way we use advanced composites, solving a problem, this time that has to be delivered in high production. Another really, really good example of advanced composites where basically it's almost impossible to compete with metal is Motomar's telescoping foremasts. And the reason is the insides of these tubes have to be dimensionally very, very close tolerance, plus or minus a half millimeter. And and these are 4 meters long, so if you had to bore out a metal tube or a pipe to the same tolerances inside, it's either really, really expensive or close to impossible to do that. Just the tools you need are amazing. But these are made on a very, very carefully made mandrel, very, very exact tolerances to the mandrel. And then we just lay up the material on top of the mandrel, and whatever the mandrel's tolerances were, basically the parts have the same tolerance. The outside is, we do have to mill the outside as well. So what happens with these is we put an extra layer, usually of glass. We'll then turn it in a lathe to make the outside perfect, and sometimes put an extra layer of carbon on top of that just for the carbon look. But this would be very, very difficult to make in metal, and the weight of it would be probably prohibitive anyway. Another very good example of a problem that advanced composites solved. All of us know about satellite dishes. If you have them on your house, you put them on your house and you forget about them. They're always pointing somewhere, I don't know, in some direction toward the west or wherever they point them, and they just stay there. But if you want to have a satellite dish on a yacht, motor yacht or sail yacht, where you got waves and the guy steering the boat, and these things always have to move around, continuously move around to home in on the satellite that's bringing in the television. So inside you have all this electromechanical stuff continually making this thing aim in the right direction. But that stuff is pretty fine stuff and has to be designed very closely. And originally KVH had these dishes made out of aluminum, and the electromechanical stuff was sometimes straining to keep up with the boat's motion. It came to us, and we basically made these dishes, again, just about half the weight, and it really made a big change for them, but it also made a big change for us, because now we've made about 400 of them, so it's good business. We also have things like standoff poles on yachts. This is a simple one. It's just basically nothing more than the spinnaker pole tube. But again, like the young man on Intrepid, the crew, when they want to put this away, they just lift it up, and 1 or 2 guys can move that pole, which is very strong, up and stow it on deck. They also have, again, like the foremast, they have telescoping standoff booms sideways on some of the more advanced motor yachts, and again, carbon fiber solving that problem. I mentioned before the tension members. We make now solid carbon rigging for our sailboats. For our sailboat clients, this is the machine that makes it on the right. You can see the difference in weight. These are equal stretch pieces of rigging. One weighs 0.8 of a kilo and the other weighs 0.2 of a kilo. So the ratio of those is around 5 again. So all you have to do is to carry around a roll of old-time metal rod rigging, and then pick up a coil of the carbon rod rigging and just laugh. It's so much different. But a really good, I think there's a wide range of possibilities for tension rods. Anytime you go to an airport, you can see steel tension members in some of the structures. And areas that really need lightweight, maybe geodesic domes or whatever, these carbon fiber rods would really make a difference in the building these things. Just a couple of other processes. Again, the matched height, elevated match temperature match molding, the method that made these Boeing pack boards, and then infusion molding. So here's the thing that makes the pack boards. You can use thermoset resins or you can use thermoplastic resins. Thermoplastic resins are really interesting and I think have a great future, although we've been saying that about thermoplastic for a while. But if you took thermoplastic, what it is, it's a sheet of cured carbon, a laminate, just flat. You put it in this machine with heat. You then form it, usually for maybe as little as 30 seconds or a minute, lift the thing up, pop out a piece that's now formed like a waffle is the only way to describe it. And if there's a problem with it, you bring it to another machine that's got no mold, just flat. Again, put it under pressure for 15 seconds and you've got the straight plate back again. You can start over with it. So it's pretty interesting stuff. The fact that you can cure a part in thermoplastic in 15 seconds to a minute means there's a real big potential for high volume production with that stuff. We also use infusion. It's just one of the things we use, but there's so many methods in advanced composites. I could go on all day about it. If I can go on all day about advanced composites, and you'd ought to be either out of here or asleep. But this infusion is that these tubes are hooked up to a vacuum pump, and it just sucks. You start out with a mold with dry material in it, and the vacuum pump sucks liquid resin in, usually much thinner or runnier than you have with normal epoxies that when you mix them up, they're kind of thick. They have to be pretty runny to get to work through this, and there are special epoxies that do it, and they're generally ambient temperature cure, but we use them for molds to make advanced composite parts in the autoclave, and making the molds, this stuff really is beneficial. This mold here, interestingly, is a wing spar for a company owned by Google called Makani, and they make this 6-engined airplane, except it's not an airplane, it's a kite, and they fly this airplane from a kite, and instead of the propellers powering the airplane, wind and motion of this kite is powering the propellers. They go to generators. Energy comes right back down the cable into a energy box or a accumulator, or energy accumulator. And then if the weather is not too good, well, you just land it and pack it up and put it in the truck and drive away. But anyway, the molds for those wing spars is what we're seeing here. And the infusion process basically was the best solution for us to do that. So again, it's only a short sketch of what we're doing. What's going to happen tomorrow? Who knows? But basically, it's up to you. So